So the examples I'm going to show you follow the examples in the textbook somewhat closely. I think that although they make sense, they take some worrying out to try to figure them out. So I'm going to try to explain or have us do one together here and talk about some of the things that people find difficult with. Discrete and continuous, make sure you think about the differences. There's a couple of good examples. I won't spend much time on it here, but you can read them through. And I put a couple of thoughts, thinking you can average numbers that are discrete, but you really don't when it comes, no, it can't be average, I got it mixed up, whereas continuous ones are meant to be sort of average to find a normal number. Let's take a look at this. Constructing a theoretical probability distribution. So we're going to use this spinner. We're going to construct a relative frequency table and graph the theoretical probability distribution. So what this means is theoretically, if you do this, where you using this spinner, and I'll explain more for it, so it's got to be, because the numbers you can see don't quite match, so I'll explain the whole problem. But we're going to figure out theoretically what should happen if you spun this lots of times, what would be the result. You'll notice on the next page, it's constructing an experimental probabilities distribution, meaning as opposed to what theory says it should be, what actually happens if you do it a bunch of times. And that's where we will use a random number generator on a calculator to do 20 trials for this one. This says 100, but I think I'm going to do this one I put in, I just made up some numbers, but I'll show you how to do it because I think it's on another one where we actually will have to do the number generator in order to calculate it. I'll show you how I got it. Okay, here. Back to this one. So, what's going to happen, we are going to do this where it's 2 spins at a time, or 2 spins. What's the result when you do 2 spins? So in other words, if I spin it once and I spin it twice, I get a certain number. It adds up to that number. So you notice for the sum here, there is no 1, because you can't get a 1 if you spin it 2 times. You add the 2 together, so there's no possible way to get a 1. You notice there's a couple of numbers missing, 17 and 19. There is no combination of the numbers on here where you can get a 17 or a 19 if you spin it twice. Okay, I thought that was interesting when I first saw this problem. So sum, and I'll put 2 spins as a reminder. So if you think about it, to get the number 2, you can spin a 1 and a 1. There is no other way to get a 2. So there's only one way that you can get a 2. So the same, when you look at the number 3, you can spin a 1 and then a 2, or you can spin a 2 and then a 1. They're the same numbers, but because your spins are different, the 2 then the 1, or the 1 then the 2, it counts as 2 separate possibilities. So for the rest of them, I figured them out, but that's the way you have to do it. You have to think, well, how many times? I'll give you the next couple and then we'll talk about 1. So let's stop at 8 and let's think about how you make 8. So if you have a problem like this kind of thing, you're going to have to think about what combinations would it do? How many ways is there to make 8? Well, 5 and 3 makes 8, and 3 and 5 makes 8. That's 2 right there. I can't do 4 and 4. 6 and 2 makes 8, and 2 and 6 makes, and let's see, 6 and 2, and 2 and 6. So that's 2 more ways. So that's 4 ways. Okay. And then 8. I have a 5 on here. What's the other way to do it? 4. I said 4, and I should have stuck with 4, because if you do 4 and 4, that's a 5th way. So you can do it, even though there's not 2 4s on here, that 1 4, because it's 1 spin and 1 again. So I had it right on my notes, and I just didn't think of it saying it right. Now let's look at 9. For 9, you can do 8 and 1, and 1 and 8. You can do 5 and 4, and 4 and 5. You can do 6 and 3, and 3 and 6, so that's 6 ways. But the other ones, you can't do anything with. So it looks like it's 6 ways. And that sometimes it comes down to, boils down to just simply trying it, thinking in your head, and thinking about how many possible ways there are. Here are the rest of them, so that we won't spend our time doing just that. So you see how to do it, and you can do it yourself on problems where you'll need to. 5, 4, 4, 2, 3, 2, and 1. Now, the relative frequency can be done in a couple of different ways. First, if you think about it, all these possible ways, there are 64 possible ones. So there's 1 out of 64 possible ways. If you add all these up, it equals 64. So there's 1 out of 64, 1 out of 32, 3 out of 64, and so on. Notice I'm leaving some space here. You can do that in fractions with all of them, but pretty soon you realize that doing it in fractions, especially since the next part of this is to graph it, that's not really going to help you with the graphing of it. In other words, turn them into decimals. Use decimals. So this one is 0.018 or something like that. So let's round them to 0.02. So we're going to go 2 decimal places with them. So 2 over 64, 3 over 64, you don't even have to reduce now if you're going to turn them into decimals. So I will give you the numbers because I've calculated these. This is another place where you just simply divide the calculator. So for 3 it's 0.05, 0.06, the number 6. It's easy to get mixed up when you have some of these, but we have to stick with 4 over 5 over 64, 0.08. This is as large as I could make these, given that I was fitting them all in on one column, or one row rather. 0.09. 5 is, or 8 is 0.08, 0.09, 0.08 again. It's nice when some of them are the same, so I can just...
Do you mind moving it a little bit?
I can. Thank you. If I run out like that, and run off it, then tell me so I can do just this and move it along. Because I'm too busy writing them and don't realize that you can't see it. The whole reason I'm writing is so you can see it. Sorry this doesn't focus very well close in like that, but it's enough hope for you to be able to see the numbers. Okay, so once you get these in, what we're now going to do is we're going to use these to graph it in order to see again where this data is. Theoretically, where you should probably, what results you should probably get if you're spinning it 2 times each. Now, we'll point out from this section. The similar one in the textbook to this does a graph like this, where it has separate, each one of these is separate event. Okay. That's a little harder to do by hand, but I'm going to try to do it anyway. Okay. So let's come down here, and let's set up this graph. On the bottom, we're going to say the sums for 2 spins. And those sums, we will put the numbers now. I actually am going to number these straight through with no breaks. I'm going to do 1 and 2 and 3 and 4. Even the ones that don't exist, like 1 and 17 and 19. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. On the y values, what we're going to do is look and see, what the numbers are. Where's the lowest and the highest? Well, 0.02, 0.03 are low. So that means that we're at 0 down here. And what I'm going to do is make this one 0.01 and 2, because I think the largest number is 0.09. So that should be near the top. That means I don't have to have it like 1 and 2 and 3. It'd be too large. We'd have everything clustered down here too much. So I'm going to make this 0.1. That means this is 0.01, 0.02, 0.03, 0.04, 0.05, 0.06, 0.07, 0.08, 0.09, and then it would be 0.1. And the title on this side is the relative frequency. So we're going to take this data, the relative frequency based on what sum you get, and we're going to graph it. I'm going to try to graph it the way that they showed for first. For 2, we're getting up to here, so I'm going to do one of these little ones like that. For 3, it's up to 0.03. For 4, it's up to 0.05. So that means that's going to this one. I'm going to put a couple of these along and then do the little dots afterwards. That's 8. This one for 7 is up to 9. Now, let's only go up to 10 right now because of the amount of time it would take to do all of them. I'm just going to have us go up to the number 10. So just go up to 10, because if you can do that much, it's clear you know what you're doing with it. Some people would prefer to leave them empty or put like dashed lines, slashes through it, saves time. You don't have to even mark it in like this. I just got started doing it and I like it. I played with a few things when I was trying different things on it. So for instance, this is what I did for one where I tried to show each one, separate them so to see them differently. And in this case, I had them next to each other rather than this. This is more the way the textbook showed it. Frankly, I don't really care as long as you get the numbers right. So there are multiple ways you could do it that would still show it right. I'm not sure that separating the bars is adding or subtracting from the knowledge of how they relate to each other. Okay. So if we did keep going with it, you would see the tail down to here. So it does show you that most of the frequencies, or most of the results, tend to be in these numbers from about 6 through about 12 is where most of the numbers are when you're spinning, when you're doing the spinner twice. Now, this is theoretical. This is if you did it and you did it, say, 100 times and it came out exactly right based upon the number of possibilities that you can have, you know, based on this being, if you did it 64 times, it should come out to this perfectly. Instead of 100, I'll just say 64. So if you did 64, it would be that. If you did 128 times, it would be double that. Theory and experience are not always the same. So let's take a look at the next page where we're going to do an experimental probability distribution. This will be a little easier with numbers, and I will show us how to do a random number generator, although at the same time I've plugged in some numbers here, and because I really don't want to do it 100 times right now. Using the sum of 2 cards randomly drawn from a stack of cards numbered 1 to 5 with replacement. Okay? So we're going to do is think, what are the numbers that you can get? We're going to construct a relative frequency table, the same thing. Okay? Now, we will say, in the textbook, the example that does this doesn't give the frequency table because this one's theoretical. So I actually put that in to help myself with how to think about it. So it's not necessary to do that one. But I did it anyway just because of the way to think about it, helping you think. All right. So we have 1, 2, 3, 4, 5. You have 5 cards. Pull one out. It's a 1. You put it back in. You pull out another one. It's a 3. So you got a 4. So that's one of the possibilities. So you do it again, and you do it again, and you do it again. So the only way to get a 2 is if you pull a 1 2 times, just like the spinner, 1 and a 1 again. So there's only one way to get a 2. To get a 3, you're going to need to pull a 2 and then a 1, or a 1 and then a 2. So there's 2 ways. To get a 4, there are 3 ways. To get a 5, there are 4 ways. To get a 6, there are 5 ways. To get a 7, there are 4 ways. 3, 2, and 1. But I'm going to put all of these in parentheses because they're only theoretical. I am not sure if we will get to, is it this one? Yes, it is, okay. If we get to 10-4, we will do the random number generator for that one because there's only 20 trials we're going to do. This one's asking for 100 trials, so we're not going to do a full 100 of them, but let me show you how to do it. Okay? So we have the possibilities of the numbers 2 through 10. Okay? So what we're going to do here is take the calculator, okay, and we're going to do math, and let's see, is it number or is it probability? It's probability. So the math button and move over to PRB for probability. Rand means random, but there's other ones. The ones we want is the number 5, random with integers. If we use number 1, it'll give us random numbers, and it'll be like 3.789512. I really don't need the decimals. I want to stick to nice, because when you pull these cards out, you're not getting decimals, you're getting integers. So let's get integers. So come down to 5, and we're going to enter the beginning number, and a comma, and the ending number. So this is going to give us a number. When I press enter, it says I got a 2. So that's, if I was doing this 100 times, I'd start marking. I just got a 2, now I got a 5, now I got a 7, and that's the way you dab it. You have to just keep pressing it 100 times and write down each one you get. It doesn't give you all 100 of them nicely in a row right at the beginning, which is what I really like. It's not quite able to do that. There are on the computer, there are calculator programs you can find that will actually do that for you. Yes?
My calculator doesn't look like that.
It will do what?
It doesn't look like that. So
That's because you have the CE, but it still should do. Oh, for you, lower and upper, put 2 there and put 10 there. That's probably what it wants. It probably wants you to separate those two. And then see how it is. You have one similar to this, but it's a little different for some commands. Doesn't do it? I'll have to look. I'll have to look at that another time. Because it's not this calculator, I'm afraid we'll have to research how to do it on that one. Okay. Yes?
Will we need to do this for the test?
Yes, but not for that many. I'm not going to make you do 100. The problem that we do on another one is, when we get to it, is only 20 times. And 20 times not that bad. Because all you have to do is press and write down 20 numbers, and that's not that hard. Okay. So yes, I'll make you do it, but I'll have a little bit of compassion. Okay. Now, I figured out 100 times, so I just randomly, it says random number generator. I decided to use my head as a random number generator and decided that there were 3 times that 2 came up, and 10 times that 3 came up, and 6 times, 12, 18. Go ahead and follow and write these down. Now, of course, being a mean math teacher, I decided to make these completely unreasonable, and large in some and small in others, but I figured just for the fun of it. But here's what you do with it. Once you have the numbers, either by using a random number generator, or in this case, just coming up with them, and this does add up to 100, so I made sure I added to 100, which is why I only had 1 left when I got to 10. You have to do, since it's out of 100, you have the relative frequency, we're going to make it a decimal. So 3 divided by 100 is 0.03. 10 divided by 100 is a nice 0.1. And so let's write out these decimals underneath each one. It's really easy when it's 100, because of course it's just moving the decimal twice. Not too hard with 20 either, because it's just multiplying by 5. But you get a calculator to use with it. Okay. So what this is showing is that 3% of the time we got a 2. 1% of, 10% of the time, we got a 3. 6% of the time was a 4. 12% of the time was a 5. 25% of the time it was a 7. But theoretically, it should have been a lot less than that. Well, that's because I made the numbers up. Actually, even if, when I did a random number generator with a number, with another one, it made the goal I was looking for a lot lower than what was expected. And I actually wrote down every number or tallied them very well, but we'll see that later on. So now we're going to graph it. Because you see this, but graphically it makes you see it in a different way. So we're going to put down here in the bottom, sum 2 cards at a time. And that sum, well, 1's not used, but we'll put it as, make the graph with, follow along logically, 7, 8, 9, and we're going to go up to 10. And then the other side, it looks like I really probably need to go by at least 2's here. So I'm going to put 0.02, 0.04, 0.06, 0.08, 0.10, 0.12, 0.14. Okay, tedious, but you got to do it. So let's get it up. Oh, now I got to 0.2 or 20, but my highest number is 0.25. Don't stress over that. Add to the graph, right? So there are times you just need to add to it. And so we're going to do that. I'm going to do 0.22, 0.24, and I'm going to put one more in order to get 0.25 in there. Just extend the graph if you need to. Now, I wouldn't do this if the numbers were much larger. If I was going into like 0.7 and 0.5 and such, then I'd probably be going up by 5s. So I would have planned that and thought about it. And that's one of the things you want to do, is you want to look at the data and sort of plan, well, what's the best way to do it? I could have gone by 5s and not had to extend it, but then it would have a lot of empty space up here, and I really didn't want to do that. Okay. Going by 3s or 4s just isn't as intuitive for most people, so it's not a good idea. You should go by 1s or 2s or 5s and 10s. Otherwise, make the graph a little different in order to larger in order to fit them in. Well, now let's graph these, and we'll do the same kind of graph. So for the number 2, it's up 0.03. The number 3 is at 0.1. So that's right up to here. Number 4 is at 0.06. Number 5 is at 0.12. 6 is at 0.18, way up here. Not as high as 7, which is going all the way up to 25, 0.25. And then 8 is 0.21. And 9 is 0.04. And 10 is really small. Now I'm going to do this time to save a lot of time. Should be consistent. I should have thought about it beforehand and not filled that one in so they'd be consistent. But now, I have not decided for the test exactly how to do it because these problems I haven't set up as test questions exactly this way before. So for this test for you, I'm not sure how I'll do, or just do a few of them or a smaller amount. I have to do part of the graph. I haven't decided yet, but just be ready to do it so that you can set it up like I'm doing, be able to determine relative frequency, use a random number generator sometimes and sometimes not use it, or I may let you choose. So we'll figure out what happens when you get it. But now you see how to do this kind of a problem. Okay. 10-3, where we're on time. Good. So let's do the third page of this one, which is expected value. Now, expected value, this one involves a good deal of calculations, okay? It's not really that hard to do, it's just tedious, and you have to really think about what to do with the numbers. So I'm gonna walk you through one problem and show you how to get the expected value. The expected value is an interesting concept in itself. It's what you expect to have returned from something that you're giving. A common example is something like a raffle or a lottery. You see a few others in the textbook, but I chose one that's a lottery in order to see it. Right now you think, well, you know, tickets are $1 each, so everybody expects to get, well, most people expect to get nothing because you're not going to win. But let's talk about the result for not an individual person, but the average. If you took what everybody gets, those that get prizes and those that don't, put it all together, what's the expected value that could be expected from one ticket? Even though, of course, it wouldn't be the full, 100,000 here. So here's what I'm going to do. So follow along and write it the way I do, so you have sort of a framework for a way to think about this kind of a problem. I am going to write prizes here. And I'm going to keep it small over here because I'm going to end up with essentially 4 columns. Okay? So I'm going to put prizes, but I'm going to use them going along. So I'm going to say that there's one prize, okay, so I guess one, or one dash or something like that. There's one prize that is $100,000. There are 10 prizes that are 10,000 based on this. Okay? 10 people will win 10,000, 25 will win 1,000 each. So 25, I guess it shouldn't be, it should be like batches like that. So they will win 1,000 each. 100 people will win $1 each. So I guess they get the money back. And 1 million tickets are sold. 125, 135, 136 people out of those 1 million people who get tickets are going to get a prize. That means the people who get nothing, if you subtract that, you will get 999,864, they get 0. Okay. X. I'm going to define X as what you get. The amount that you get, well, this person won $100,000. That person paid $1 in the first place. So they didn't really get $100,000, they got $1 less. So what they actually got was $99,999. Each of those 10 people, they didn't get 10,000 each, they paid $1, so they'd already lost $1 before they got their prize. So they really got only 9,999. And these people each paid, was it 1,000? Yeah, so each of them lost $1, but, so it's 999, okay. And these people lose $1, which means they actually get nothing. They get $1, they paid $1 and they get $1, so they're just breaking even, nothing more. And all the rest of the people paid $1 and lost it, so not only, it's not that they don't get a prize, they actually are down $1. So they're all at a -1. Okay, now, what we're going to do, the way they write this is up. Okay. This one, where I'm going here, so is Px. So as a function, okay, so the amount of the prizes, I should say, or I'm not sure how to say it. Let me show you what the number is going to be. It's going to be one person over the amount of people, the total amount of people. So one person gets this prize out of the 1 million tickets. We call it P of X, although it doesn't quite work as putting this number in and resulting in that. But let's do it. This one is 10 people over 1 million people. So 10 out of 1 million get that prize. 25 out of 1 million, it gets tedious, like I said, another 0. This one's 0 out of 1 million. And this one, oh, wait a minute, it's one.
Yeah, shouldn't that be?
Oh, you're right. I got myself lost and looking at the wrong thing. So it's 1, 10, 25, and it's 100 people. And then this last one is 999,864 over 1 million people. So what we do now, the last column here is we're going to multiply these two, x times p of x. So it's 99,999 times 1 over 1 million, which is really just this divided by that. This one times 10 divided by that. This one times 25 divided by that. This one is actually, because of the size, this one comes down here, that one goes down here. 0 times that, that's easy. This one's going to be 0. -1 times that. So, you can put them in the calculator and get the decimals, but I already did that. We're going to round them. 99,000 times 1 divided by 1 million comes to approximately 0.1. It's like 0.9986, something like that. Okay, so it's 0.1. This one, 9,999 times 10, well, that makes it very similar to this, divided by 1 million. So it actually is, because it's 10 of them times it, it's about the same, 0.1. When you do 999 times 25 and then divide by 1 million people, that's there too, you end up with 0.025. It's actually like 0.0248 or something like that. So you round it. You have to pick a reasonable place to round it. Well, this one, it's this divided by that times the -1. It comes out to -0.999864. Makes sense? Okay. What we do with this is we add them up. Add all of those. So it's this plus this plus this plus 0 minus that. And what you get is -0.7748. So I'm going to let everybody catch up and we'll talk about the significance of that. Come all the way down here. So think about what we did. The number of people getting prizes, the amounts of the prizes that they get, the actual amount of money they get, because you have to subtract 1 from each, the number of people over the total number of tickets, so 1 over a million, 10 over a million, 25 over a million, so on. Multiply those to get these decimals, and when you add them up, you get this number. I'm going to round that so close it should almost be 78, but it's really not. It's 7.0. So I'm going to say that, and I'll write it this way. The expected value is -0.77, because that 4 will round that down. I could make that a 5, but it's still the 48 isn't enough to make that an 8. So that's approximately that. Well, what that negative means is it's a loss of 77 cents, because all these decimals mean amount of money. So it means the expected value. So really, you have an expected, or there is an expected loss of 77 cents for each person. The person getting the $99,999, he's getting a lot, or she's getting a lot. Somebody's getting a lot of money. A lot of people are losing $1. Well, when you take all those prizes and spread it out evenly with everybody, it doesn't make up for everybody losing $1 as well. So that means the average for everybody, basically the average for all million people getting the ticket, is losing 77 cents. So that means this lottery company is making lots of money off of them. You know, that's basically getting 77 cents for every person. Now you can figure out how much that would be, but that's you know, pretty good. That's what, 770,000, I guess. So, yep, so they're making some money. So, and that's the way lotteries often work. Sometimes you see, and some examples I have seen, they'll have a situation set up like this, and they'll show like some group is doing a lottery, but the way they set up the prizes, the expected value comes out to like 12 cents, positive 12 cents. That means that they're ending up paying more money than they're getting from the lottery, which is not a good thing if you're trying to raise money. You want to make it so people have a reason to think they're going to win something, but you can't let them win so much that you don't make anything, so your company or the charity or whatever it is just lost on it, and that wasn't the goal. This is maybe a little high, but still. Okay, that's how expected value works. You see that the numbers, it's not really complicated multiplying, it's just that complicated thinking about what the steps are. Subtracting one from each of the amounts, doing the multiplying, recognizing that you need to do this kind of multiplying, with arrows here to show the thing with it, and then adding those up and then recognizing what it means. Okay, so overall, this is a pretty complicated kind of problem, but you now see and recognize what you can do with it. Okay, I'm going to put these aside. Okay. Those are 3 pretty big problems to do. I certainly am not going to give you all 3 in the same way on the test. I'll have to figure that out and let you know. But now you have an idea what to do with those.